OCR A A-level chemistry, module 4. Let's go. The first thing in this part of spec is naming. Now, it is really long to explain this, so I'm going to be honest, the best way to learn naming or to practice learning is to do exactly that. Practice, questions with it in. That being said, when you have a carbon chain, all your carbons are numbered from left to right or from right to left. And when we start adding groups, your main goal should be to keep that number in front of the group as low as possible. So if you're going for an alcohol on what I've labelled 5 here, it would actually be hex 2-ol because it's in the second from the shortest side. But we'll go over that in more detail when we come to the actual functional groups themselves. So some definitions. General formula is the simplest algebraic formula of a member of a homologous series. You'll see it like CnH2n plus 2 for alkanes. Structural formula means that you put the minimum detail into showing the arrangement of the atoms in a molecule. So rather than writing C2H6, you write CH3CH3. Displayed formula shows the relative positioning of atoms and the bonds between them. This is the one with all your C's and your H's and the lines between them. Now, skeletal formula is the simplified organic formula shown by the removal of the hydrogen atoms from alkyl chains, leaving a carbon skeleton and functional groups. Now, that's a whole lot of words, but I can sum up what it means for you now. Basically, every carbon is a dot, and then you draw lines between the dots for your backbone. That's what it's saying, carbon skeleton. You ignore the hydrogens completely, and the only thing you draw in is any functional groups like alcohols or alkenes, things like that. Now, a homologous series is a series of organic compounds that have the same functional group, but each successive member differs by CH2. And a functional group is a group of atoms responsible for the characteristic reactions of a compound. Now we're moving away from the English part and we're moving towards the actual chemistry. So we have an alkyl group, and what that is it's the general formula CnH2n plus 1. These will fit onto your carbon chain at different positions, and their names are just like the name of the group. You take the ane off of your alkane and you add an YL on the end, and that's your name. So you have methyl, ethyl, propyl, butyl, and I've never seen more than butyl on a question. You can classify hydrocarbons in 3 ways. Aliphatic, which the definition is on screen now, but basically if you see anything that doesn't contain a benzene ring, as long as it contains carbon and hydrogen, then it's aliphatic. If it doesn't contain benzene, but does have some sort of hydrocarbon ring, then we call it alicyclic. And then finally you have aromatic, which is anything containing a benzene ring. You can also classify them as saturated or unsaturated. Saturated contain only single carbon-to-carbon bonds, whereas unsaturated will contain multiple carbon-carbon bonds, like double bonds, triple bonds, even sometimes. Now, it specifically notes in the spec being able to use the general formula to predict the formula of, different members of a homologous series. And all that's saying is, if they give you a functional group, like an alkene, spot the pattern, which is the general formula, and then use it to fill in the gap that they've given you. So for alkenes, we know that it contains C2H4 and C3H6, so we can say that it's CnH2n, and so for C5 it would be C5H10, and that's all it's asking you to do. Occasionally you end up with something called structural isomers, which are compounds that have the same molecular formula, but they are different displayed or structural formula. So C4H10 can either be butane or it can be methyl propane. Now, if you're struggling to understand that, I've got a video on isomers on my channel, so definitely go check that out, obviously after you finish this one. So when you have a covalently bonded molecule and it starts to break down, you can either take one electron from the bonded pair and give it to one atom and then one to the other, which we call homolytic fission, or you can take both of them and give them to one of the atoms, which we call heterolytic. Now, homolytic fission creates 2 radicals. Now, what are radicals? Well, they are a species with an unpaired electron, which we represent with a dot here. So you can see a chlorine radical here because it's Cl dot. And you can show the movement of an electron pair using the curly arrow. because it's an electron pair, you can use this for hydrolytic fission or the formation of a covalent bond. Now, you can also use curly arrows for reaction mechanisms. Now, reaction mechanisms are really, really important, and they're worth a lot of marks on an exam, so make sure you pay attention. Now, alkanes are obviously saturated because they only contain single carbon-to-carbon bonds, and so they contain sigma bonds. This means that they can rotate freely, as you can see here. Now, if you don't understand what sigma bonds are, don't worry, we'll get into it later. Because they only form single bonds, the carbon can bond to 4 other atoms, which gives it a tetrahedral shape, which is in one of my other module recaps, so make sure, again, if you don't understand, you go and check it out when you have a moment. Now, the general rule with alkanes is the longer the chain, the higher the melting point, and that's because they've got more surface area to act with London forces, so the London forces are much stronger. But if you start adding branches like methyl or ethyl groups, they start to get in the way, and so it lowers the melting point the more branches or bigger branches you put in it. They are very low reactivity, and that's because they've got a really high enthalpy, because sigma bonds are not very polar at all. Now, you need to know what happens when you combust them, but that's easy. You chuck in some oxygens and you get out carbon dioxide and water. Obviously, in the exam, when you've got an actual alkane and not just the word alkane, you try and balance it. The spec specifically mentions incomplete combustion forming carbon monoxide, and then it asks to go into the dangers of carbon monoxide. Now, carbon monoxide is very dangerous because it doesn't smell bad or anything, but it is very toxic and it can cause fatigue, headaches, dizziness, and in really extreme cases, death. Okay, here you go, your first mechanism. So this is radical substitution, so make sure you're paying attention. So there are 3 steps in this. So there's initiation. So here you're turning a chlorine molecule into 2 chlorine radicals by homolytic fission. Then you have propagation. Here you're using your alkane, which is reacting with your chlorine radical to form an alkane radical and hydrogen chloride. Your alkane radical then reacts with chlorine again to form a chloroalkane and a chlorine radical again. And now you have termination. Now, termination can be any one of these reactions here. Basically, any 2 radicals react to form a stable molecule. As you saw there are many limitations. You can generate a mixture of organic products. There can be further substitution, so that's when your chloroalkane goes through the process again to become a dichloroalkane, and then possibly a trichloro, tetrachloro, etc., etc. And also you have the risk of creating isomers. We just say reactions at different positions on the carbon chain because it sounds nicer. Now, alkenes are unsaturated hydrocarbons, so they contain carbon-to-carbon double bonds. Now, carbon-to-carbon double bonds consist of a sigma bond and a pi bond. A pi bond is a sideways overlap between 2 p orbitals. Sigma bond is just the overlap between 2 p orbitals, so a sigma bond is a lot stronger than a pi bond. Double bonds contain both sigma bonds and pi bonds, which makes them stronger than a single bond. And also because of the pi bonds, they have restricted rotation, as you can see here. Now, it's important to remember, even though there's 2 bonds here, it is one bonded region, i.e. it still forms trigonal molecules. Now, because of this restricted rotation, it demonstrates something called stereoisomerism. Now, stereoisomers are compounds with the same structural formula, but with a different arrangement in space. This means if you attach group to your carbon-carbon double bond, then this molecule and this molecule are different because they can't rotate. The one with the 2 groups on opposite sides we call E, and the one with the 2 groups on the same side we call Z. Now, we can also call them trans and cis isomers, but this isn't always the case. It's only the case when 2 of the substituent groups are the same. Now, when the groups aren't the same, we use something called the Kahn-Ingold-Prelog principles, and this states that the higher the atomic number of a group, the higher the priority it is. So in this example, carbon has a higher atomic number than hydrogen, and oxygen has a higher atomic number than hydrogen, and so we call it a Z isomer. Now, alkenes are very reactive, and that's because pi bonds are polar, so they have a really low enthalpy. Because of this reactivity, you can perform addition reactions, where you add hydrogen with a nickel catalyst to create alkanes. You can also add a halogen to create dihaloalkanes, which a specific example the spec says is with bromine, which is obviously the test for alkenes, so it will turn bromine water from a browny kind of orange to colourless. You can also use hydrogen halides to create haloalkanes. Adding steam in the presence of phosphoric acid will give you an alcohol. Now, you need to know this word, and it's electrophile, and the definition with it is an electron pair acceptor. And you can use these in electrophilic addition, which is another mechanism, so listen up. So, this is what it's supposed to look like. Obviously, the curly arrows are a transfer of electrons. This forms a positive ion, which we call a carbocation. Then finally, you chuck on the bromide, and you get bromoethane. Determining the carbocation formed is down to something called the Markovnikov principle, which says that the carbocation formed is as high a priority as it can be. When your cation is attached to one carbon, we call that a primary. When it's attached to two, we call it secondary. When it's attached to three, we call it tertiary. And stability increases going down this list. Because there is a double bond in alkenes, you can turn it into a polymer through something called polymerization, and this is what a polymer repeat unit looks like. Polymers need to be processed, and the spec asks you to learn how to process certain wastes. So you can combust them for energy production, or you can use them as a feedstock. So you use them to make other products. Now, you have to remove toxic waste products like hydrogen chloride during disposal through combustion. Now, biodegradable polymers have microorganisms in them that eliminate these toxic residues, and they can either be an additive to the plastic, or they can be natural found polymers. Or they can be photodegradable, which means they are weakened by sunlight, which starts the degradation. Now, it's important to know, not all polymers are biodegradable or photodegradable, but all of them can be combusted or can be used as feedstock. Now, moving on to alcohols. Alcohols have the functional group OH, and we can also call this a hydroxyl group. Because of the OH group, alcohols have dipoles. Because of the OH group, they could also form hydrogen bonds, and this means that they have a higher melting point than their alkane counterpart. So methanol has a higher melting point than just methane. Now, because of the OH group, they are also highly soluble in things like water or other polar solvents. Now, alcohols aren't very volatile at all. They don't react very well. And just like carbocations, you can have primary alcohols where the carbon is attached to 1, secondary where it's attached to 2, or tertiary where it's attached to 3. Combusting alcohols will give you the same as combusting anything else in organic chemistry. It will give you carbon dioxide and water, and obviously if you have this question in an exam, you'd need to balance it. There are different reactions for primary and secondary and tertiary alcohols. So when you react a primary alcohol with an oxidizing agent, which is probably going to be potassium dichromate, which you can see here, you're going to get an aldehyde and water. Now, in order to do this, you need to distill it. We'll see what distilling is later, and you also need to add an acid catalyst. I've used here sulfuric. If you were to reflux it instead of distill it, you would end up with a carboxylic acid and water. And again, you'd use a sulfuric acid catalyst. With a secondary alcohol, you create a ketone. Now, you cannot oxidize a tertiary alcohol because the bonds are too strong to react. Now, you can also dehydrate alcohols, and like the name suggests, this is when you remove water. And you do this using phosphoric acid and heat, and it creates an alkene and a H2O molecule. Reacting sodium halide with an alcohol gives you a haloalkane. You can test for the type of haloalkane using sodium nitrate and ethanol. At 60 degrees Celsius, iodoalkanes form a yellow precipitate, bromoalkanes form a cream one, and chloroalkanes form a white one. Now, if you were to do these all at once, they would come out at different times, and you can see the order at which they come out here. So iodine is the fastest and chlorine is the slowest, and that's because as you go up group 7, your carbon to halo bond becomes much stronger. This is another term you need to know, nucleophile, which means electron pair donor. And then here comes the mechanism that comes with it, nucleophilic substitution. So you can see it here. It's how you get from haloalkanes to alcohols. Now, haloalkanes can be a problem because of something called CFCs, which means chlorofluorocarbons. In the mid to late 20th century, these were used as deodorants, refrigerants, and aerosol propellants. Obviously, chlorine here acts as a halogen, so it creates some sort of haloalkane. Now, in the atmosphere is a molecule called ozone, which is represented as O3. A haloalkane, when it reaches this layer in the atmosphere, forms radicals like we saw earlier with radical substitution. This radical reacts with the ozone to form oxygen molecules, just regular O2. Now, this is a massive problem because ozone absorbs UV from the sun, but oxygen doesn't, and it just lets it through. And that causes massive problems for people. It can cause skin cancer, cataracts, and crop blights. This process can form chlorine radicals, which go off and do the same thing. So you end up with a lot of the ozone layer depleting and deteriorating. It doesn't just have to be chlorine, it can happen with things like nitrous oxide from lightning strikes or aircraft, but the process is still the same and the reaction still looks the same. Now, this is reflux, and I've labelled all the equipment here. This is what it looks like, and you should have done this practical in class if you're doing A-level chemistry. If you're not, this is something called glassware. The reason the water flows up the Liebig condenser is so it surrounds it and doesn't leave little air bubbles in it, so it cools it completely. What this does is if you produce gas in your round bottom flask, it goes up the Liebig condenser, cools, and goes back in, so it stops you losing gas as a product. This is distillation, and it does the exact opposite. It heats the flask, so your gas is produced, and then it goes into the Liebig condenser, condenses, and comes out as a liquid. And it's really good for separating certain products that have different boiling points. Now, if they have similar melting points, you can use something called a separating funnel. Now, these will have different densities, and so one will float on top of the other, and you'll have an aqueous layer and an organic layer. And the way you can tell which one is which is you add H2O, water, and then the aqueous layer will thicken, and then you know which one is which. Then you put it into your separating funnel, which you draw a diagram of like this. You place your thumb over the top kind of stopper thing, and then you invert it like I'm doing here, but with a whiteboard pen rather than a separating funnel. And every now and then you're going to release the pressure by opening the tap and add a little bit of water just to thicken the aqueous layer. After you've done this quite a few times, you can then separate them into two different beakers, one with your aqueous and one with your organic, and obviously label them, because if they're not different colours, you're going to have a really difficult time if you can't tell the difference. Now, some of your organic layer might still have water in it, so you use something called a drying agent. There are 3 examples at the bottom there. You can use any of them, so I just recommend picking one and sticking with it, so you know it off by heart for your exam. Now, if water's present, the drying agent will clump in the middle of the flask, in which case you add more drying agent until it disperses and it's just a fine powder in the bottom of the flask. And then you can redistill it with a narrower boiling point, to separate them. So now we need to learn about spectroscopy, and the first one is infrared spectroscopy. Now, when infrared hits a bond, it vibrates, and different bonds will vibrate differently. And so you can find out about the bonds in a molecule using the infrared spectroscopy of that molecule. This is what an IR spectrum looks like, and the thing that's past 1500 is called the fingerprint region. Now, you don't need to know about this, it's unique for every molecule, and realistically, when they do it in real life, they use a computer system to recognize it. Now, you can look at the peaks, find out what number they are, and then look at your datasheet, and that will tell you what functional group they are referencing. So just here we've got many peaks at 3000 and one peak at 1600. This is an example and it doesn't correspond to anything, but if it did, you could find out the group there and you could say, oh, it's a ketone or an alcohol or whatever it might be. And the spec also specifically mentions that the absorption of infrared light is the same reason that some organic compounds like carbon dioxide or methane are such strong greenhouse gases. Carboxylic acids obviously contain a hydroxyl group and a carbonyl group, but it's important to know that it will have both, and it will have a broad OH peak rather than just an OH peak. Now, it also mentions there are many other uses for infrared spectroscopy, including breathalyzers and emission checks on like cars and factories and things. You've also got to learn about mass spectroscopy. Now, I mentioned this in Module 2, but this is slightly different because it's bigger molecules and not just elements. Now, you can find the relative molecular mass using something called the M+ ion peak, and this will be a relatively big peak, and it will either be right at the end or one before the end. Now, if it's a tiny peak compared to all the others, then it's just a result of a carbon-13 isotope, and it is not the M+ ion peak. Now, different isomers will have different peaks in different places with different intensities, and so you can use mass spectrometry to differentiate isomers. For example, here you have the OH group from the left-hand side and the C3CHOH group from the right-hand side, and these will create different mass peaks at different places. But 17 is very unlikely to occur in the right-hand side molecule, and likewise 45 is unlikely to occur in the left-hand molecule. You don't have to, you can calculate them, but I would recommend memorizing these three groups here, as they're likely to come up on something like a mass spec. Some of the molecules are split, they create carbon radicals, and these don't show up on the mass spec. If there's a peak missing, then that's why. You will be expected to use mass spec, infrared spec, and information given to you in a question like empirical formula or molecular formula to find a certain molecule. So that's going to be it for today. I hope you enjoyed it and I hope it helped in some way. Please like and subscribe, and I will see you next week for Module 5. Thanks, bye.